So as a reminder, what did we talk about last time? Well, we spent a lot of time doing an example. Oh, maybe too much time. But you know, you should do an example like that at least once in your life. And then we actually spent about 20 minutes talking about what we were supposed to talk about, which are matrices. And we're talking about matrices because matrices are a very nice way to represent some systems of differential equations. And in particular, the kind of differential equations that are somewhat reasonable to approach. So those are linear systems of differential equations, and more particularly first order. And we'll see that as we get towards the end of today. But for now, we're still going to build up on sort of some basic tools in matrices, things that we can use. So as a reminder, what are they? Well, initially when you see a matrix, a way to think about it is you have this array. And so you have an array, it has indexed by rows and columns, and you can fill it full of stuff. And you can put in things like numbers, you can put in something like functions, you can even put in things like operators. So when we talked about sort of our method of elimination, one of the ways we did it was say, oh, if we fill our matrix with operators, then we can use something very similar to Cramer's rule to solve. And there's some things we talked about. For example, how do we pick out an entry? Well, we use subscripts. So the ij is really a locator here. So it says look in row I, column j, and whatever is there, we call that aij. And we said, all right, but we want to start doing math with these. So we said, all right, well, let's start with some simple stuff, arithmetic. How do we add? And we said, okay, well, we can add matrices as long as they're the same size by just making sure we add the corresponding entries together. So in other words, if I have matrices A and B, and they're the same size, if I want to say what ends up in row I, column J, I say, well, go to A, grab the entry in row I, column J, go to B, grab the entry in row I, column J, and add them together. You can also scale matrices. And so that's, think of C as maybe a number or maybe a function, depending upon where we're at, but something times A. And the way we do that is we do it each entry. And we're like, wow, this is easy. Working with matrices is super fun. You just say, look, I'm just doing lots of problems simultaneously, one for each entry. So I can add, I can scale, I can start taking what we call linear combinations. And the nice thing is because we're doing it entry by entry, and we have all these wonderful intuitive things about the way that addition and scaling works, things like it doesn't matter what order we add. A plus B is B plus A. We can also think about subtraction. And we say, oh, A subtract A, that should be like 0. And so we said, oh, let's make a matrix called 0. The 0 matrix, all the entries are 0. Nice matrix. It has the property, if I add the 0 matrix to any matrix, it's the matrix I started with. So it does what we want. And life was good. And then we said, let's multiply. And then life got interesting. And we said, well, look, multiplication doesn't work the way that we may intuitively think it works. Because we say we're going to abandon doing it entry by entry. And so here's how it works. So what we do is, suppose I have two matrices, B, A, and I want to make a new matrix that's the result of their multiplication, B times A. And I want to say, what's in this entry, the ij entry? So that's what we're saying here. What's in the ij entry of this matrix BA? And the way you do it is you say, come to the first matrix, and if I'm in the ith row, I grab the whole ith row. And if I'm in the jth column that I'm looking at, I say, grab the whole of the jth column. And now what you do is you're going to actually use the whole row and the whole column to produce this entry. And you just go term by term, dot, 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 multiply and add. Multiply, 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 add the result all together. So that's what's happening here. See, this sum, and whenever you see a sigma, think of that as adding. Sigma starts with S. Sum starts with S. So sigma for sum. And here we're just saying overall possibilities. And so when I look at something where it says B-I-K, that just says move along that ith row. Because the I is the row and K can move along. A-K-J. Well, the J is fixed. That's the column. And then k can move along. So you're moving down the column. So you're moving along the row, down the column. Multiply, add it all together. That's also known as the dot product. All right. Well, it's not too hard to make some observations. So for instance, here, if I move along a row, how many entries would I have? In other words, what's the number here? Well, the entry is number of columns. Because I'm in a row, so I'm going to have the number of columns show up. As I move down, if I fix my column and move along, what will I see here? Well, I'll see the number of rows. And so what we have to have is that when we're multiplying two matrices together, and this is what you see below here, is that the number of columns in the first matrix has to match the number of rows in the second matrix. So these have to be the same. If these two numbers are not the same, then forget it. You can't do multiplication. It doesn't make sense. But as long as those numbers are the same, it does make sense. And so you can have really exotic looking rectangles. So you can have strange rectangles multiplying together. As long as the number of columns of the first equals the number of rows in the second, life is good. In the output, you'll have the number of rows from the first matrix, number of columns from the second matrix. Now you might be looking at this and saying, well, that's a little strange. And yes, multiplication is strange. And so if you haven't been convinced already, we will convince you in the next few minutes as we look at examples and saying, that doesn't look right. Well, that's because you're trying to think of multiplication as the way you're used to it. And we'll see, you got to abandon some of your old ideas and preconceptions. All right, one last thing we talked about, and then we'll get going for today. I said, all right, well, suppose I have this multiplication. I'd like to have something that acts like a 1. Now, 1 is a special number, because 1 has the property, it's called the multiplicative identity, and that means that if I multiply by 1, I don't change anything. So I want to have a matrix, if I multiply it, it doesn't change anything. And that's called the identity matrix. So you should think of I and identity as being 1. It even kind of looks like a 1 when you write an I. So that says A times I times A, it's A. It doesn't change anything. All right. So that's what we did last time, other than say that multiplication is strange. But we kind of felt that. So that shouldn't be too surprising. So we're going to start with some examples. All right. So we have two matrices here. 2, -6, -1, 3, and 1, 2, 2, 4. We're going to find some various values. A times A, which we're going to write A squared, B times A times B. Now, we should point out, we can really find A to squared, A cubed, A to the fourth, so forth and so on. So we can find A to any whole number. And it just means keep multiplying by A enough times. So you can take lots and lots of matrices and multiply together. All right, so A times A, or A squared. Now, keep in mind that in order to do matrix multiplication, there has to be some sort of compatibility. Number of the columns in the first one has to match the number of rows in the second one. So you can't even multiply a matrix by another matrix if there's this incompatibility. But in this case, since they're both 2 by 2s, you can multiply 2 by 2s by 2 by 2s as much as you want. You'll still end up with a 2 by 2. Oh, I'm sorry. Oh, I was getting ahead of myself. I was so excited. This is the trouble of trying to talk and do math at the same time. It's like trying to math and do talk. It's just very difficult to do. Okay. So, there we go. All right. So, we'll go slow on the first one, and we'll speed up a little bit as we go on, because we'll do more examples. So, when we get this, the end result, we've already said, we'll have 2 rows and 2 columns. So really we have 4 entries we have to fill in. So we're just going to do it entry by entry. So if I want to get the entry here in the first row, first column, I'm going to go along the first row and down the first column. So 2 times 2, 4, minus 6 times minus 1. 6. 4 plus 6, 10. Now, first row, second column. So first row, second column. 2 times minus 6, minus 12. Minus 6 times 3, minus 18. Minus 12, minus 18 together, minus 30. Second row, first column. So second row, first column. Minus 1 times 2, minus 2, minus 3 times, 3 times minus 1, minus 3, put it together, minus 5. Second row, second column. Second row, second column. Minus 1 times minus 6, 6. 3 times 3, 9, put it together, 15. All right. So it's not so bad. Once you do a few of these, there's sort of a rhythm. It's like, okay, I move along the first row in first matrix. I move along the column in the second matrix. And it flows. It flows. Okay, B times A. 1, 2, 2, 4. 2, minus 6, minus 1, 3. Okay, 4 entries. Let's see what we get. Okay, so 1 times 2, 2 times minus 1, minus 2, which 2 and minus 2 gets 0. It's okay to get 0, right? Minus 6 plus 6, 0. Oh, that's okay to get 0. 4 minus 4, 0. Minus 12 plus 12, 0. Okay, now this matrix here has a name. It's called 0, the 0 matrix. So remember when we said multiplication is strange? This is an example. Now, why is it an example? Normally when we multiply two things together and we get 0 out, think back in our old setting. When we're multiplying two things together and 0 comes out, what had to be true? One of them had to be 0. That was like numbers. We're in matrices. It doesn't have to be true. I can multiply non-zero things and 0 can come out. Oh, strange. Strange thing number 1. But the strangeness continues because matrices are beautiful and exotic. All right, so let's try A times B. 2 minus 6 minus 1, 3. 1, 2, 2, 4. Now, before we start, our intuition, if we were thinking about numbers, what should be true? It would be like all zeros, right? Because it says, oh, it doesn't matter, right? A times B, B times A. Let's check. All right. 2 times 1 is 2. Minus 6 times 2. Minus 12 put together. Minus 10. Now, that's not 0. What? Okay. Finish it up. 2 times 2 is 4. Minus 6 times 4 is minus 24. So that should be minus 20. 1 times minus 1 is minus 1. 2 times 3 is 6. So that should be 5. Minus 1 times 2 is minus 2. 3 times 4 is 12. Put that together, that should be 10. And notice, they're not the same. These do not equal each other. So it can be the case. Now, I'm not going to say it's always the case, but it can be the case. And in fact, I might even say it's often the case, unless you have something really nice happen, that A times B is not the same as B times A. There are some cases where it is true, but this is our way of saying, be careful. A lot of the things that we're used to with multiplication, well, we take for granted, but they might not be true in this new setting. So be careful and just take your time. You'll be okay. You'll be all right. All right, any questions about multiplication before we move on? Well, okay. So if we can multiply, what's the next thing we want to do? Divide. And so that's the next subject, which is about inverses. And so what is that? Well, if we have a matrix, we can think of the inverse of the matrix as something we'll write as a to the minus 1, and we think of it as dividing by a. And in particular, what it means, we say b is the inverse if a times b equals b times a equals the identity. Think of it back in terms of numbers. So what would we say is the inverse of 2? A half. Well, what's special about a half? Well, it's 2 times a half gave us 1. And 1 is that magical number. We call that the multiplicative identity. So I is acting like our 1. So we're looking for is something multiplying by a that gives us back to our setting of 1. So that's why we call it the inverse. You'll notice there's a statement highlighted. Not all matrices have inverses. Now, why? Well, actually, we can go back really quickly. I'll convince you that we've actually seen a matrix which doesn't have an inverse. So here's a quick example. We talked about this matrix 1, 2, 2, 4. That was the example we just talked about. And remember how we said 1, 2, 2, 4 times 2 minus 6 minus 1, 3 was the all zeros matrix? Let's suppose C was this inverse. Just for a second, suppose it did have an inverse. Well, if I multiply C by 1, 2, 2, 4, then because it's the inverse, that would be the identity matrix. If I multiply C by the all zeros matrix, well, what's true? If I multiply a matrix by 0, what should I have? I should have 0. So that says the right-hand side is 0, but the identity matrix has a special property. Identity times anything is the anything. And then we say, okay, so if this matrix did have an inverse, we would have to be the case that this matrix 2 minus 6 minus 1, 3 was the matrix 0, 0, 0. But is that true? No. So in mathematics, we would say that's not true. But really, in our heart of hearts, we say, no! That means that something was wrong. And what was wrong was this assumption. So this is how we can show that not everything has an inverse, because if we did, we'd reach these impossible situations. All right, so not everything has an inverse. So how do you know if something does have an inverse? It turns out there's a couple ways. The easiest way for us, in terms of the tools we have, is you look at the determinant. So the determinant, we've talked about it before. We'll talk about it again in just a moment. But the determinant can capture whether or not something has an inverse by asking a simple question. Is the determinant 0 or not 0? If the determinant is 0, no inverse. If the determinant is not 0, inverse. Now there's other ways to talk about it. There's this notion of linear independence. But that can get more complicated. Let's just stick for determinant for the time being. So how do you find an inverse? Well, it turns out that there's a nice little procedure. And the procedure is going to be helpful, not just for finding inverses, but for doing other things. So it's good to practice it. And it says the following. Take the matrix you're looking for the inverse of, and we're going to make this sort of augmented matrix. In other words, we're going to sort of like make it twice as long. So we're going to take the matrix we're trying to find the inverse of, and next to it we're going to write down the identity matrix. And then we're going to go and start to manipulate. The goal will be, I want to make the matrix on the left look like the identity. But I'm only allowed to do 3 things. And they are, well, 2 of them are pretty simple. We'll start at the bottom. You're allowed to swap any 2 rows. And you're allowed to multiply a row by a non-zero number. The other thing you can do, which is the number 1 on the list, it's actually the most important, says I can add a multiple of 1 row to another row. Now, we can actually talk about these in terms of like linear systems of equations. So swapping 2 rows, it says if I have 2 equations that I'm trying to solve, I just write them in a different order. Like, okay, that seems fine. That doesn't really change anything. Multiplying a row by a non-zero number says, oh, I don't like the constants here. Maybe I want to get rid of fractions, so I multiply through. Like, okay, all right, that's fine. That's something you can do. Now this one about add a multiple of one row to another, we've actually been doing it quite a lot, but we just haven't done it in this setting. And so this particular rule, in fact, this rule is so important. It should have a star next to it. It's like the most important rule. In fact, a double star. And where have we seen it? Well, this is when we have two equations and we're like, oh, let's multiply the first equation by like -2 and add it to the second equation and get something to cancel. That's what's happening here. It's the same principle. It's not just a similar principle, it's the same principle coming into play. And so this gets lots of stars. Very important idea. All right, so let's go through and do an example. Now, the punchline is, after you take the left-hand side and make it look like the identity, the right-hand side, which started with the identity, is the inverse. So, we're looking for the inverse of this matrix. Now, what tells you we're looking for the inverse of this matrix? Find that little thing, right? So the -1 power means you're looking for an inverse. So, we begin. We begin at the very beginning. It's a very good place to start. All right, so we take our original matrix, write it down, and then to the side we write down the identity. And remember, the identity matrix is the one where it's 1s down the diagonal and 0s off the diagonal. So our goal is to make the left-hand side look like the right-hand side. Okay, and the best way to do this is just try to be systematic. And I like to think about going column by column. You know, channel the character from the Lord of the Rings movies. You know, column, column, column. All right, so 1, 0, 2. If I want to make this look like the identity, what do I need to do to this column?
Make it 1, 0, 0.
I want to make it 1, 0, 0. So I like the 1, I like the 0. I want to get rid of that too. I want to make that as a 0. Well, what can I do with my row operations that let me do that?
Add a multiple of one row to another.
Yeah, add a multiple of one row to another. Which row?
The first row.
First row. Which multiple?
-2.
Okay, so we're going to multiply the first row by -2 and add. So that's what I'm indicating here with that little arrow. Now, what happens to the first 2 rows? Nothing happens. The only thing that changes is the last row. Okay, so when we say multiply by -2 and add, every single entry is being multiplied by -2 and then adding it down. So what does the new row become? The new third row. -2 plus 2 is 0. And then -1, because it's -2 plus 1. Okay. -12 plus 8. -4. Keep going. -2 plus 0. -2. 0 plus 0. And 0 plus 1. All right. Good. So we've gotten a little bit closer. And now we're like, we like that first column, lock it in. Next thing is we say, time for column 2. What can we do to column 2 to make it look like the identity? So in particular, what should it look like? 0, 1, 0. So what can we do to this? And we can do several things at once, or we can take our time. Not too much time, we have other things to talk about. Okay, multiply -1 by what? By the second row? Okay, but let's say, let's just embrace it. Multiply -1 by, how about we multiply -1 by the second row, right? Because that's a -1. We want a positive one. So we can I'll just write -1 here, just in case I'm multiplying. And so that'll be a really quick step. So I just flip the signs all the way across. but nothing else changes. All right, that makes the entry there a 1. That's good news. How do I get these entries to be 0 that aren't there? You know, this first and third entry.
Add the third row to the first row, and then the first row to the third row. Well, no, the second row to the third row. Excuse me.
Oh, wow. Okay, interesting. Interesting. So you're saying add the third row to the first row, and then you want to add the second row to the third row. Yeah, we can do both those. 2 at once. All right. So what row doesn't change? Yeah, the middle one at the end won't be changed. Okay, so that's good. We can just start by writing that one down. Okay, how about the first row? So we're adding the last row to the first row. What will we have? We'll have 0 plus 1, minus 1 plus 1, minus 4 plus 6, minus 2 plus 1, 0 and 0, and 1 and 0. Yes? What will become on the bottom row? What will we have? So we're adding the bottom 2 rows together. The first entry?
0.
Next entry?
0.
Next entry?
Negative 1.
-1, good. Next entry?
4.
-2. Next entry? And final entry? 1. All right, what's next? Now, you might be thinking to yourself, we have to find like the correct step. And here's the fun thing. There's many correct things you can do. So it's not like there's one single path. Ultimately, the goal is let's move closer to getting to something that looks like the identity. Notice the first 2 columns. We're like super psyched, like yes, yes, no, not yet. So our focus is on that third column. And we're like, okay, got to focus on the third column. Say, okay, what can we do to that third column to make it look better? And by better, what do we want this to look like? 0, 0, 1. Okay, so what can we do to make this look like 0, 0, 1? Just, what's one thing we can do? Okay, so they're like, this last row, let's make that -1 a +1. So we'll fix the sign. Now, I will warn you, you're like, wow, this is cool. Everything always turns out to be nice whole numbers. No. But I wanted to have something where I didn't have to deal with fractions. I'm not really a big fractions fan. Don't tell my irrational friends about that. But I try to avoid fractions. Okay. Most of the times when you do this process, you'll have to get fractions. But all right, for now, we had a nice example. Okay, so we got the 1. We now just need to clean up. How do we bring it home? What can we do? Okay, -2, third row, the first row. Yeah, okay. So this is just, we're being methodical here. And we'll just do it right next here to the side. All right, so last row, we're not doing anything to. So that stays as is. Okay, let's do the middle row. So remember, we're multiplying the bottom row by -3 and adding 0 and 0, 0, 0 and 1, 1, -3 and 3 is 0. Okay, what comes next? -6, because -6 plus 0 is -6. And then -4, and then 3. Okay, first row. Again, you'll see that this side is going to be nice because we set up that way. The 0 and 1, 0 and 0, the -2 and 2, and we're like, ooh, nice. Identity. Okay, last part. What do we have? So remember, multiplying by -2, adding. Negative 4 plus negative 1 makes negative 5. Negative 2, 3. So we got to the identity, and so our claim is that we're finished, and that A inverse, so if we're calling this matrix here A, whoops, so if this is A inverse is this matrix, negative 5, negative 2, 3, minus 6, minus 4, 3, and 2, 1, minus 1. Now, can we check our work? Yes. Well, you can always check your work by redoing it, but suppose we didn't want to redo it, and we weren't even convinced that this was going to work in the first place. There still might be some skeptics in the audience. What can we do to convince ourselves that this is, in fact, the inverse that we're looking for? Yeah, we multiply them together. So that's what we'll do. Now, if we don't get the right thing, then we'll know we made a mistake. But if we do get the right thing, we'll be like, wow, this is so cool. I'm going to become a math major. Well, maybe not that, but at least it'll be like, hey, the mathematicians aren't so bad. They know something. Okay, here we go. We'll go through this quickly. Minus 5 minus 6 plus 12. 1. Minus 2 minus 4 plus 6. 0. Looking promising. 3 plus 3 minus 6. 0. Nice. Next row. 0 plus 6 minus 6. 0. 0 plus 4 minus 3. 1. 0 minus 3 plus 3. 0. Okay, last row. Minus 10. Minus 6. That's a lot of minuses. Plus 16. 0. Minus 4. Minus 4. Plus 8. 0. 6 plus 3 minus 8. 1. So it works. All right. So it works. At least it worked in this one time. It'll always work. Now there's a couple of things you might say. And you might say, but what if I had made a different set of choices? Would I still end up with the same answer? What do you think? Yes. Yeah, this is somewhat of a choose-your-own adventure where the endings are all the same. Some paths might take longer to get there, but you'll always end up with the inverse. Now, a more subtle question you might ask is, why does this work? Okay, so I'm going to give you a little bit of a hand-waving explanation. Don't worry, you don't have to memorize this. This is like a week in linear algebra class done in one slide. So what we're really doing is we're starting with the matrix A and I, and we're doing the same thing at each step. And at each step, what's secretly happening is we're multiplying by a little tiny matrix. So step 1 says, hey, I'm multiplying by a little tiny matrix. I'm doing it both to A and I. And I do the same thing again in step 2. And I keep going and I keep going until I stop. And once I stopped, I said, well, if I put all these little matrices together, that's a new matrix called B. And B times A was the identity. Because I got down to the identity. That's when I stopped. Well, if B times A is the identity, that means B is the inverse of A. But now what happened over here? Well, over here, I did the same thing. So I really have B times the identity, which means that on the right-hand side, all I had was B. So that's why when we stopped, on the left-hand side was the identity, on the right-hand side was the inverse. So that's a week of linear algebra in one slide. You don't need to know that. That's just why it works. I like to know why things work. Okay, any questions about inverses? Good. We will do this process again. Maybe not the full process of finding the inverse, but this process where we use these steps will show up again. Not today, but soon. All right, now determinants. And determinants are going to be pretty quick because we've actually talked about determinants before. The idea is we start with a square matrix, we take the determinant, and out comes a single value. So it's like I have this array of numbers, and the determinant is trying to capture something, and I'm just trying to figure out what it is trying to capture. It's a number. And so we know how to take the determinant of a 2 by 2 matrix, AD minus BC. And we also know something called cofactor expansion. We've talked about this before. I think at least we waved our hands. This is technically how you do it for larger matrices. I would say don't worry too much about it. As long as you can do 2 by 2 and 3 by 3, you're fine for this class. So if you know how to take 2 by 2 and 3 by 3, you're fine. Just there are technical things where we can do it. If you're wondering what does it mean to do cofactor expansion, well, the idea, and I probably should have planned this ahead of time, says you pick your favorite row or your favorite column. It doesn't really matter which row or column. Let's say we go along the ith row, and we go entry by entry. And so you'll see there's a sum of k. So k is moving along this row. And what you do is you take that entry and you cross out, so this is the kth column, you cross out the kth column, you cross out the ith row, and you have a slightly smaller matrix. And you take the determinant of that. So this is what you see here. This, what looks like absolute value, is really saying the determinant of that matrix AIK. And now you multiply that by the entry here. So that's this little AIK. And then, to make sure people are sufficiently confused, we put either a plus or a minus, depending upon where we're at. And the way you figure out is you add I plus k. And if I plus k is even, it's a plus. If I plus k is odd, it's a minus. And so you work your way through. And that's how you can do the determinant. And essentially what that tells you is that you can find the determinant of a large matrix by finding the determinant of smaller matrices together. Okay, so that's the idea of cofactor expansion. But I would say for 2 by 2 and for 3 by 3, just know how to do the formulas by going down diagonals, and that's usually the easier way to go. So for example, for 2 by 2, we oftentimes think of it as AD is that diagonal, subtract BC is the other diagonal. Now, you might be wondering, what is the determinant trying to capture? It's a value. Does that value have a meaning? It does. So remember we talked about how we can think about matrices as moving from one place to another place. In other words, these are called linear maps. Well, when we have a square matrix, which is where we're at, we can actually think about moving back onto ourselves. So I can think about, I'm mapping my coordinates back into my space, but I'm doing things like stretching, twisting, shearing. And so in particular, I can think about what happens to this nice little unit square. Well, it'll transform a square into a parallelogram. And if I know where these two corners map, because 0 will always map to 0. Always. So I can say, well, where do these two corners map? They map to somewhere. The last corner follows the parallelogram. You know, it has to follow and fit there. The determinant is this area. So in other words, it's capturing how much area is there after you map that unit square. That's the underlying geometric intuition. Now, you might ask a quick question. Why do we have it signed? And the answer about why we have it signed is because there's this plus minus. Whenever we're in mathematics, plus minus really refers to orientation. So you should think of plus as going forward, minus going backward. Or there's a type of orientation reversal. And similar, if you think about it in terms of physics, you'll often hear about the right-hand rule. And if you flip your orientation, that would be the left-hand rule. It's just a way of saying there's a different orientation in place. All right, so that's the matrices part of today. And we should take a few minutes and do the calculus part of today. Because, you know, this is basically a calculus class. We should mention calculus at some point. So the calculusy part comes in and says, we can start filling these matrices, or these vectors, with functions. And we can start asking things like, what about derivatives? What about integrals? What can we do? And the answer is that we do what we think should be true. Now the nice thing is, to take derivatives, we need to add and scale and take limits. Those are the three things. Adding and scaling, we've talked about how do we add and how do we scale? What's the rule? Entry-wise. And limits, same idea, entry-wise, which means when we take derivatives or we do integrals, we just do it entry by entry. So in other words, it's the same kind of stuff we've done before. We just have to do lots of little problems, one for each entry. So let's go through and find these derivatives. So here, x of t, I have really 3 entries. So to find the derivative, x prime, we just go through and find the derivative of each slot. What's the derivative of arctangent? 1 over 1 plus t squared. You kind of suspected that might be my first example. The derivative of natural log of e to the t plus t to the 4th. So whenever you see a natural log, you're taking derivative, you should think about how the derivative of natural log works. Normally, derivative of natural log is 1 over. So it's 1 over the inside. So we write the inside downstairs in the denominator. Is that it? All right, what else is involved? Chain rule. So the chain rule says we multiply it by the derivative of the inside. So the derivative of the inside goes on the top. What's the derivative of e to the t plus t to the 4th? E to the t plus 4t cubed. All right, derivative of t sine t. What would that be? Sine of t plus t cosine t. Okay, that sounds right. What rule is this? Product rule. So it's really the same rules because everything's happening entry by entry. So there should not be too many surprises. All right. What's a prime? Well, it's a 2 by 2, so now we're going to have 4 entries. Derivative of e to the 2t. 2e to the 2t. Derivative of cosine t. Negative sine t. Derivative of 12. 0, because it's a constant. Derivative of t squared plus 3. 2t. So taking derivatives, no problem. We can do that. On a side note, just for fun, suppose I was taking the derivative of the product of 2 matrices, A of t, B of t. What do you think this should be? Just what feels right? You would think it should be A prime of t times B of t plus A of t, B prime of t, right? Because, it's like, that feels like what the product rule should be. And in actuality, it is. So product rule still works the same way if you're dealing with matrices. So good. But you have to make sure you keep the order the same. Don't mess with the order. All right, well, if we can do calculus, well, that basically means we can do stuff with derivatives. And stuff with derivatives, that's like the name of our class. You didn't know it when you signed up. I didn't know this was stuff with derivatives. But that's it. Okay, so prepare for a wall of text. As a reminder, you can download this. And this is going to be like, whoa, too much information. But then you start and say, wait a second, we've already talked about everything here. Isn't this just the same? And the answer is, yeah. This is all the stuff we've talked about before and just slightly tweaked. So this shouldn't feel really that different. So we start our discussion by saying, hey, suppose we have a differential equation. X prime is A of t. Now remember, here x prime is not a function, it's actually a vector of functions, where we've taken the derivatives. A of t isn't just a function, it's a matrix of coefficients. X is, again, a vector of functions, particularly the vector we're looking for, and f of t is a vector of functions. But it looks basically like the same thing we talked about when we talked about linear first-order equations. So there's a couple things that we can say. First off, we say, let's focus on the homogeneous case. Now, the homogeneous case says this little part on the end, set it equal to 0. So the homogeneous case is x prime equals a of t times x. And it says, suppose you have some solutions to that case. Then what can we do with them? And the answer is we can combine them together and get new solutions. This is the idea of superposition. Superposition saying I can take a bunch of solutions and combine them together and make new solutions. This is what we did before. But then we say, okay, are these good solutions? And we go back and say, well, what does it mean to be a good solution? Does each one give me something new? Have I gained something from that solution? And we call this linear independence. And we say, okay, well, how can we test? And in particular, what does it mean to be linearly independent? It says, if I look at any combination of them, and I were to get 0 out, the only way I could do it is if each individual coefficient were 0. That's the technical definition. But really, the idea is, when we say that they're not linearly independent, I can get one of them by combining the rest. Well, there's a test. And we use the Wronskian. But it's slightly different here. This is probably the biggest change. So it used to be when we had the Wronskian of individual functions, here's the Wronskian of a list of functions, and we form a matrix. The first row of the matrix was our functions. The second row, what went there? First row is function, second row is? First row is, next row is? And so forth and so on. Now, we're changing it. And here's the change. If I have a bunch of functions, I'm going to make a matrix where the first column, this is a vector, right? First column is the first vector. Second column is the second vector, all the way to the last column, which is the last vector. But you have to have the number of functions has to equal the number of entries in these vectors. Because we're taking a determinant. It has to be square. So the Wronskian now just says take those functions, throw them into a matrix, take the determinant. If the determinant is 0, then you don't have a good set of solutions. If the determinant is not 0, and when we say not 0, not identically 0, it's a wonderful set of solutions. It's exactly what we want, linearly independent. All right. Well, now we can talk about things like the general solutions. Where it says, suppose you have a nice set of linearly independent solutions. And this is, you have n solutions. It's a system with n equations. Then every solution is a linear combination. So this is, again, the same thing that we had before. Just says, if we have a nice set of solutions, combine them together, you get all solutions. Well, we've talked about homogeneous up to here. How do we handle non-homogeneous? Now, previously what we did was we said, all right, if we have a non-homogeneous equation, we did 2 steps. First, we found a particular solution. Then we found the solutions to the homogeneous equation. And finally, we put it all together. Now, in this setting, what we're going to do is we're going to find a particular solution. We're going to find solutions to the homogeneous equation. And then we're going to put them all together. Now, if you feel like you just had some deja vu, good. Because it's the same idea, same process. And the last thing is we can handle initial conditions. Now, initial conditions here are, we have like a column of saying at time 0, where are all the functions at? And then we can solve for our initial conditions. When I say solve, it means find these coefficients. So all the ideas we've had before translate into this new setting. Now, I have a little bit of time left. I know you think I don't. I have a good solid 15 seconds, which means we're not going to do this one today. But we will start here next time. All right, have a good day.